Hello everyone, Srikash here with my teammate Shashank. This is the video for homework 3 for the course Design and Analysis of Reconfigurable Systems, and today we will be demonstrating a working and usage of Intel IP modules for calculating sine and cosine of an angle using CORDIC algorithm. As you can see, I've already opened the Quartus and created a project with no files currently. Go to the IP catalog and search for CORDIC. Now open the IP. Create the name with the IP variation sincos and click OK. Now go to the input data widths and set fraction as 10 bits, width as 13, signed input. And the output data fraction as 5 bits and the width is 7. Double click on Altera Codic and open the IP generator. Create the entity name with sine cos and click OK. Set the input fraction bits as 7 and output fraction bits as 3. When you're done configuring your CORDIC IP, click on Generate and generate HDL. Create simulation model for Verilog also and hit Generate. Close the IP generator and go back to Quartus. Now, to include the generated IP, go to Project, add or remove files in the project, then search for the QIP file in the syncos synthesis and syncos.qip. Click on Open, Apply, and OK. As you can see, all the necessary HDL files are included for the CORDIC IP. Additionally, include your SDC files for timing constraints. Now, set your sine cos module as top level entity. Go to hierarchy and compile your design. When the compilation is done, go to assignment and pin planner and assign your pins to the respective locations on the board. After compilation is complete, go to Analysis and Synthesis. Go to Resource Usage Summary. Here, the total ALMs used are 112, combinational elite logic used are 214, dedicated logic registers used as 168, and IO pins are 22. Note that the stats might vary when you assign pins differently on the board. Now, go to timing analysis, open timing analyzer, go to custom reports and report timing. Here, as you can see, the slack is positive with 16.455 nanoseconds. And for the critical path, report path. Here the delay is 9.081 nanoseconds. Now close the timing analyzer. Now go to files, go to project, add or remove files in the project, and add your test bench file. Here I have written a small test bench file that iterates the angles from 0 to plus pi, and after reaching pi, it starts from negative pi and goes back to 0. Let's see the simulation using RTL simulation. Now, compile your design along with the HDL source file generated by the IP generator. Simulate your test bench using sincos. Add your signals to the wave. Change the radix to your custom fixed point radix. Set simulation time to 10 microseconds and run the simulation. Now select the signals which contain fractional bits and format them in analog mode with automatic setting. As you can see, the input is varying from 0 to pi and then negative pi to 0 again. Simultaneously, the cosine and sine values are being calculated by the IP as follows. Close simulation. And continue with the program device, open programmer to flash the design to the FPGA. So the design has been loaded onto the FPGA. Now switch on the device. Hit reset. For example, the current value is pi. So the upper 5 bits are cosine and lower 5 bits are sine. So when I hit the switch, sine pi is 0 and cos of pi is -1, as we can see in the LED array. Let us try another example. Keeping all values to 0 and we try it again. So the cosine value is 1 and the sine is 0. Let's try one more value. Let us try sine 30. As you can see, the sine 30 is 0.5 on the top 5 bits and cosine is 0.875. For the second part of the assignment, I have edited some of the code so that we can observe our cosine and sine outputs at 7 segment displays. Here, the top module is sine-cos hex.v. As you can see, it has the CORDIC IP instance along with few debouncers and a toggle switch so that we can switch between the outputs at the 7 segment display LEDs. And it includes a segment decoder which converts your 5-bit fractional input to displayable LED format. Let us now see the contents of segment decoder. Here, the input is 5-bit sine or cosine value calculated by the CORDIC IP, and the output is sine, the integer value, and the rest of the fractional bits. And they are decoded as follows. Similarly, going to the hex decoder, the input is the value, which is the decimal from 0 to 9, also includes the sign, negative sign and null value so that no LEDs are displayed. And the output is the 7 segment display LED wires that are connected to the 7 segment displays on the board. Now, compile the design. After the compilation is done, go to Analysis and Synthesis, then see the resource usage summary. As you can see, the ALMs used are 123, the combinational Elliott logic used are 229, logic registers are 191, and the IO pins used are 56. Now, go to the timing analysis, open timing analyzer, go to custom reports, report timing, and the slack is positive. And for the critical path, go to report path. So the critical path is from A reset to one of the inputs of the sine course with a delay of 10.19 nanoseconds. So the maximum operating frequency is 1 over 10.19 nanoseconds. Close the timing analyzer. Open the pin planner after compiling the design and assign your pins. Here I've already assigned my pins respective to the pins on the board. Now flash the design onto the FPGA using program device to open the program. After flashing the device, as you can see, with the current input being 0, the primary value shown on the LEDs is cosine. So cosine of 0 is 1, and if you want to flip the output, we can flip the output with this switch and we can see the sine. Let us try another value. For example, try sine 30. Now hit this button to calculate the sine value, sine and cosine values. So by default, this is cosine value of 0.875 for 30 degrees, and for sine it's 0.5. Let us try for pi. Now calculate the value of sine and cosine at pi. By default, the cosine value of pi is -1, and to flip the output, just toggle the switch and the sine value is 0. So we have successfully verified our CORDIC IP with the help of 7 segment displays.